seconds sooner.
Go to me. All right, so let's get started. Welcome to our nearly last TWed of the spring 2016 season. We're welcoming Spencer Norris, our only undergraduate speaker our undergraduate superstar speaker. All undergrads who speak at TWeds are superstars, right? So, and actually, Spencer's got big shoes to fill today because he's going to be describing the SemNExT project, which he is part of, okay? And he's going to talk about it as if he is Evan Patton and Deborah McGinnis and Kristen Bennett. It's going to be great. But really, Spencer's focus is going to be on the work that he actually contributed to it. So, and we'll be kind on the other things. A couple logistical notes. This is being streamed live and persisted forever on the interweb. So keep that in mind. So feel free to ask questions, but keep it in mind that your questions are going out to the web. A couple other logistical notes. There is a datathon. The Rensselaer Idea Datathon is happening in a weekend from next. Instead of a normal TWed next week, there's an information session that will be happening up at CII. Food for teams that have registered for that.
Okay, so no TWed down here.
No TWed here. In the TWed time, actually an hour later, it's going to be 7 p.m. There's going to be this information center up in CII. We will distribute that information. If you've got any questions about the datathon, if you somehow have not received an email through the department or any other ways yet, you will surely receive it. There are 10 teams signed up so far. It's very exciting. Top prize is $2,000. Top prize is $2,000. Top prize is $2,000. Anybody actually on a team so far? Yes. So Kristen Bennett says her students are going to win that. So there's your challenge right there. And she's not judging because she wants her students to win, and she wants. So anyways, thank you guys for being involved in that, and it's going to be exciting. So I think that's it. Oh, and the week following, so 2 weeks from today, there's going to be we haven't decided what to call it, but it's sort of it'll be here. It's going to be sort of a datathon retrospective. It's not a postmortem. Because of the scheduling, we're actually not expecting the participants to actually show up. But we're going to be talking, it's going to be sort of about hands-on learning with data, datathon as an example, that kind of a session. So it's not specifically focused on the datathon, but it's going to hold up the datathon as an example of learning through this sort of big data analysis. Tom Morgan and I are going to lead that one. So without further ado, Spencer, take it away.
There we go. Thank you for the introduction.
And I'm going to run upstairs and get some tea.
Okie dokie. So like John said, I'm an undergrad, so go gentle, please. I'll do my best to answer any questions you guys have at the end of this, but feel free to interject if there's something that you want a little more detail on in the meantime. So I guess we'll hop into this. Oh, sorry. There we go. Okay, so background on what SemNExT actually is. It's sort of a mesh between a whole bunch of interdisciplinary fields, mostly new ones, some old ones. Numerical analysis isn't anything new, but the idea of meshing that with semantic data and allowing the semantic data to drive those analyses is, and then applying that to a application area like bioinformatics gives it another twist. So we kind of went into this project asking the question of whether or not you would be able to create a framework that allows you to easily integrate numeric analyses with semantics and allow that to be done regardless of the application domain or the type of data that you're going to be working with. And I think it's going pretty well so far. There's more work to be done. But I'm going to give you guys a brief overview of what's been done to date, and where we're going and some of the tooling that we're using under the surface, as well as how this can be applied to other things. So I guess I'll talk about some of the systems that are underlying SemNExT and how it actually works as a web service. So it's built mostly on open source technologies, which makes it very redistributable. Basically, it's built almost exclusively on Python with embedded Sparkle queries and little smatterings of Bash throughout. So a lot of the core libraries that are being used, CherryPy, RDFlib, these aren't crazy fringe libraries. These are pretty widely used. We use R2Py to be able to link the framework back to the actual numerical analyses that we want to do. How many people here know what Docker is? There we go. So for the people who don't know, Docker is basically an application container that lets you take scripts, throw them into an interface that allows them to be interacted with by whatever protocols that you specify. It's just a quick and easy way of basically building web applications. And then Docker Compose is the way to build a whole bunch of those Docker containers into a larger network that can communicate with each other. It's especially useful for doing the data sources because you basically take a whole bunch of different Docker containers, use the top level container to load the data from another one into your instance, and then get rid of these two guys. So yeah, Docker is super useful for what we're doing because this is reliant on a whole bunch of different subsystems. Anyways, we basically take all these different systems, take an internal ontology that allows us to link all of our different data sources, and then we create a Python object model that mirrors the ontology so that we can actually manipulate the objects on the inside. Yeah, right.
How long does it take for you to incorporate that
To build the ontology? Kind of depends what methods you're using, I would assume. So the ontology, this is getting a little bit ahead of myself, but the ontology is all built on Bravo. So you have a base point that you want to start with, and the object model all kind of flows down from that. But it's going to be basically dependent on what the data sources are that you want to use, because you still have to resolve the schemas internally. Actually, I think this is well, another slide. But yeah, it's going to be completely dependent on what kind of application that you're looking to build. Yeah.
So the links in ontology, are the links in ontology basically the same as in this moment merge data sets, and you will specify different things are same. So I presume, because I didn't get a chance to see the ontology itself, but I'm just curious if those links are.
Right. You'll want to use same as links under the surface. And it's again kind of dependent on what you're looking to do. But you're also going to wind up using this ontology to annotate different objects with different RDF types. And a lot of that will be able to drive the linkages between the data sources as well.
Maybe you can come back to that.
Yeah, I'll be
I think
talking.
you should come back because there will be a bunch of subclass relationships and not all the same by any stretch.
Right. So moving on in the meantime. So kind of how SemNExT, so I described it as this network of Docker containers. You are going to have the SemNExT service kind of contained within its own Docker container, communicating with everything else though. As far as how that's actually working under the surface, you basically start with the data sources that you want to wind up using. For our application, we have a few different options. We have Unified Medical Language System. We have BioRDF, redrugs. So you basically create data source objects that abstract the interaction with those data sources away. Use the internal ontology basically to create the mappings that we were talking about between those different objects. And then from there, use the Python object model to manipulate those entities on the inside. So once you have this data model constructed, you're able to basically feed them to these annotator objects. And the annotator objects are where we're going to do a lot of the actual mapping. So you'll be able to feed the data model object to the annotator, and it'll have predefined rules on the inside to decide what do I do with this particular object. Then basically you'll be able to call on an analysis object, which is also a subclass of one of the prov objects. And you'll be able to feed the data model objects that you've decorated with the annotators and generate new results from that, or vice versa. You can call the annotators after you've done your analyses. Again, this is highly modular. There's no predefined workflow, but this is what it'll typically wind up looking like. So this is just kind of a graphical representation of what I was talking about. You can see the data sources that we're using for the project right now along the bottom. And these are all externalized. So we have MySQL instances that contain StringDB, Ensemble. UMLS is contained on the mobile health servers at the TWC. We also make calls out to redrugs, which is a safety service. And anyways, we have basically two subclasses that are used to interact with those right now, database source and Sparkle source. Now, I mean, obviously there are things other than just, MySQL instances and Sparkle sources. So you're going to be able to subclass the data source object so that it's a little more modular and you can interact with these data sources in a uniform way according to what your needs are. But anyways, basic idea, feed these data source objects over to the annotator. Annotator will be able to use the analyses and decorate the results or the inputs before it goes out to the analysis. Bring it back and feed it back up to the end user with the SemNExT API. In our use case, we're also using visualizations, which I'll talk about a little bit later. Of course, this isn't necessary for using SemNExT, but it's very useful for our purposes. Again, we'll talk a little more about that in a few minutes. So just a little more on the ontology. Like I mentioned, you're just using it basically to link the object models of the data sources to each other. My understanding is that it's generally more useful to have a more expressive ontology in this context because it's going to make your mappings a little more rigorous and make sure that your data is a little prettier when it's going into the system. Garbage in, garbage out type situation. You want to basically make sure that your results are consistent. So it makes sense to have a strong ontology underlying SemNExT. So the Python object model is kind of reliant on these 6 separate classes. I'm going to delve into each of them other than cache. Cache, it's interesting. It's built on Redis, which is another one of the external services that we spin up in the Docker container. And we use that basically to store up all of our intermediary results and anything that we might want to reference again. But it doesn't really deal so much with the semantics, which is what I'd rather focus on right now. So I guess I'll start with the Provenance Object, since that's kind of the top level object that overlays everything else in this model. Like I mentioned, it's basically designed to mirror Provo, and we use the Python class's attributes to mirror the Provo model. Fairly simple mapping, but very useful for manipulating things inside of Python without having to create new instances inside of the triple store. It's non-exhaustive because it really doesn't have to be in this situation. Again, we're only manipulating certain attributes in certain classes that we're worried about feeding to our different objects inside of the object model.
Wait, so by non-exhaustive, you just mean it's not modeling all of Provo?
Right, right. I mean, we're only taking a few of the classes that we really need, like prov entity, prov thing,
Okay.
Yeah, the ones that are really going to be important for modeling other things in this ontology, like downloads, data sources.
Okay.
Now, the data source object, its subclasses, I believe, prod entity. And like I mentioned, this is just a way of abstracting how you interact with a particular data source under the surface. And you basically subclass this according to what type of data source you're interested in working with. We have the two predefined ones that I mentioned earlier, the database source and the Sparkle source. The Sparkle source uses embedded Sparkle queries and has a URI attached to the class. And basically you just use the embedded queries, target it at that URI, and it'll feed the results back into a RDF graph. And then you can parse those for whatever results you're particularly interested in. A lot of this stuff in the meantime is hard-coded. We want to eventually incorporate the rules engine that will make the manipulation of the results a little bit easier, but I'll talk about that towards the end. There are other caveats that I mentioned, like I mentioned earlier. Redrugs happens to be one of those. I'm going to have to actually define a separate subclass to deal with redrugs properly, because right now it's sitting inside of a Sparkle source. Because we use it as a Sparkle source in some instances, we're actually querying the redrugs endpoint, but then it's also a SADI service. Do you guys know what SADI service is? So SADI service basically is just a semantic web application that uses HTTP. And you can feed it RDF graphs and pull RDF graphs just using HTTP post. And it'll expect a certain type of class and it'll output a certain type of class. As it stands, the sources that we have defined at the moment aren't really designed for just strict HTTP communication with the service. So going to have to make a class that does that a little more rigorously, but still allows the functionality of the Sparkle source so that we can query the endpoint as well, if that makes sense.
But I imagine if you implemented the interface for SADI, then everything that's a SADI service potentially could be hit.
Could potentially be a what?
Get accessed.
Yeah, that's the basic idea. Just create a generic but a consistent way of interacting with these for the future. So I could probably just build that into the permanent structure of it, which would make sense. So any other questions so far? Did I lose anybody? All right. So the data model objects, again, just mirroring the ontology that's underlying this entire system. For what we've been doing, we have data model objects for clusters, for specific diseases, specific genes. But again, this can be generalized to really anything, because you're literally just creating a Python class that has the attributes of the prop object. So it's simple enough. But you also use the data model object according to how you want to manipulate your results on the inside of SemNExT. So we have something called a semantic array. This is something that Evan came up with, and the basic idea is that you want to be able to create a one-dimensional or a two-dimensional array of numerical results, and then you want to be able to attach the provenance to that. Additionally, you want to be able to reference this once you throw it back into your triple store. So you give it a dereferenceable URI, something that you can refer back to this whenever you need to. Now the semantic array is what's actually being fed into the numerical analyses as they stand right now, which I'll talk about momentarily.
And did you say what a NumPy class is?
Oh, NumPy class. NumPy is another Python library. This just extends one of its internal classes. Can't remember the name of it right now. So, Anteater Objects. Now these are what are, at the end of the day, probably going to be the intermediary between the SemNExT API and your data sources. The basic idea is that you should be able to send a call to the SemNExT API, and it'll have a method that calls the annotators, and the annotators will actually do the composition of the results from the data sources. The way they're designed right now, you decide for yourself, what am I interested in connecting between these data sources? Am I interested in garnering a specific result? And the annotator will issue a SPARQL query against the designated data source according to what you're interested in. Ooh, the screen looks very pretty from but anyways, so one of the annotators that we have designed right now, this is something that needs to be fleshed out a lot right now, and is probably going to be an important part of the next iteration of the service. But one that Evan defined so far is the SPARQL type annotator. Basically, feed it the URI you're interested in talking about, and just look for other RDF types that it matches against. This is particularly useful for when you're looking at the internal triple store that you've set up and the ontology that you have. So you can say, oh, well, I have this particular entity that is an ensemble gene. I can also say now that it maps pretty well to a redrugs gene or a string DB gene, depending on what you're looking for. Again, depends how you structure the internal ontology. But the annotator is basically a way of using the internal ontology to your advantage when you're manipulating the results of the data source. You look like you have a question.
Well, it's anytime you talk about type, there's always big question marks. And what's really interesting is there's sort of this, for this work in particular, are we talking about sort of a data type from a Python perspective morphed into this, or are we talking about something else? And so that's not meant to get an answer. That's just a question that's going through my mind. So being able to find things by a specific type is very useful. But in this case, what exactly do we mean by what are examples of the RDF type properties? How does, I mean, is it, I think you may have just given an example there.
Right. So off the top of my head, I can't think of anything in particular that uses the RDF type predicate. I think a better way of talking about this might be to pose another example of what an annotator might be able to do.
Okay.
That might be a little more powerful than just linking types. You might be looking for different aliases for a particular gene, for example.
Mm-hmm.
So you would say, okay, I have this particular URI from, say, redrugs, for example, and I have a label attached to that URI. Can I go to UMLS now, use that label to look for the other names for this gene that appear there? Great. If I can do that, now I can issue SPARQL queries using those alternative labels against other objects after I attach it to this Python object that I fed to the annotator. Does that kind of make sense?
Oh no, that's very powerful. I mean, that's a really good example. It seems like it's the purpose ultimately is to sort of expand, broaden the reach of what it means to, when you go looking for a particular type, you actually find things that are synonymous with that, or not synonymous, but equivalent. So,
gotcha.
I mean, that's pretty, okay, that's good enough.
I think it's pretty cool. A lot of work to make sure that this is very rigorous and well structured first, but once it's done, I mean, like I said, that's going to be kind of the next step for the project, I think.
It's that kind of that semantic mediation role.
Right, and if you do this at a really general type, it's going to just give you so much that it's not going to be worth it.
Right.
But I think actually it is going to be pretty beneficial, kind of in the mid-level of specificity.
Right. Yeah, that's kind of what I was thinking too, and why it's very important to have a rigorous ontology underlying the system. So, continue. Okey-doke. So the analysis objects are again another subclass of provenance objects that we had defined. The top level analysis object isn't designed to be instantiated on its own. It's just supposed to provide a generic template against which you can define other types of analyses, but that captures the information from the prop class again. So the way we use it right now is that we have an R analysis, and what the R analysis does is actually provides a concrete way of operating on whatever object that you're feeding it. In this case, it should be the semantic array. So you're supposed to basically subclass it, define a concrete way of interacting with the object that you're feeding it, and a way of getting the results back to the user with the provenance intact. You could probably do this very easily with other numerical analyses tools like MATLAB. I don't know if there's a Python library that does that. I'd imagine it would be. But again, just a very simple way of tying these objects that we've created in the internal data model over to the analyses, calling those and getting them back. And this is kind of where R2Pi comes in. So for Umbrella, like you have a question.
No.
Okay.
No, I think this is actually pretty. No, that's this time I was just, as you talked about this, I was just curious for the punchline, how you were implementing, whether you're using R script or whether you're using something like R2Pi. So that's cool. I was curious how you were calling R from Python.
Yeah, fair enough. And a lot of this I'm not touching because I'm not a mathematician. This is where the Department of Mathematical Sciences actually comes in. We just kind of take what they use and then build it in. But talk about that briefly.
And they use both R and MATLAB, but only focusing on the R at the moment.
So as far as extending the API and using all of these tools that I just described, it's actually fairly simplistic. This is probably the easiest part. Once you're done defining your data model, making sure that's logically consistent, building all of these Python classes, this is where you actually just get to use what you've already built, and you probably have a very rigorous and well-defined way of using these going in. So building the API, it's built on CherryPy, so extremely simple to actually do. You just add a second method, basically to an init file that sits inside of SemNExT, and just tell it what annotator or what data source you're interested in calling, manipulate the results, and then just return that. And CherryPy will actually automatically encode that as JSON LD once you return. So it's a very simplistic way of getting people clean results based upon whatever you're interested in. Pretty nifty. This is especially useful since a lot of this JSON data you can feed back to external visualizations, like what I was talking about earlier. But get there momentarily. So this is just revisiting the original diagram that I showed you earlier. Just hoping that this gives a little more sense of how these actually start to tie together now. So the example might be that the SemNExT API, you're looking for, in our case, a whole bunch of different gene clusters. So it would percolate down to an annotator, look for what results it actually needs to combine between different data sources based upon predefined rules. Take those results, put them in a semantic array, and throw that in an analysis object. Pull that back up, throw it back up to the API, and send it to a remote user. If that makes sense. Any questions so far? Okay. So the motivating example for how SemNExT is being used right now has been on neural stem cell data. And this is where the Department of Mathematical Sciences kind of comes in, and the work that we've been doing with them. So we've been using a lot of the data sources I've talked about so far, particularly, I think, StringDB, Unipro, and running analyses on the results from there, creating gene clusters, and feeding that to the types of visualizations that you see here. This is a coordinate heat map diagram. This was designed by another undergrad, I think, Matt Boygel. I would not have been able to do this. Basically, what it does is that if you look at the green and red rim that runs all the way around that, those are heat maps that are radiating out from the center that show the activity of a gene during a particular phase of the cortical development cycle, which is just your brain growing. And we can basically do clustering analysis and look at the activity of the particular genes, and then create almost a clock of what is active when. All those chords that you see in the middle are basically connections between different genes and their co-expression. And the colors represent different layers that actually emerge during the development of the brain, and relate particularly to the co-expression of the genes. Again, I'm not sure how much I can talk specifically about the analyses that underlie that, but the results of this has basically been that they've, well, not basically, it's pretty impressive. They're able to identify another layer in the cortical development cycle that had not been previously identified, the neuroectoderm, which can be seen as orange in the coordinate heat map diagram. You can see it's particularly prominent in microcephaly, which is a symptom of Zika virus, which has been in the news recently. But this was actually garnered, I think, 6 months or so before that hit the news, something in and around there. In effect, though,
well, we didn't tie it to Zika. All we did was we found out that microcephaly formed in this very early time window of development. And then we later found that Zika messes with some proteins that are quite prolific in that window, which is, and it's a scary time because it's before women typically know they're pregnant. But if you get infected with Zika, the chances that Zika messes with these proteins, I think, is extraordinarily high. And if these proteins are messed with in this time window, it's extraordinarily highly likely that you're going to get microcephaly, which is a devastatingly awful disease.
And all of this is going to be discussed in an upcoming publication.
Yes, yes.
Right.
Sorry, didn't mean to imply that we linked it directly. It's like not Zika, not my intention. But anyways, just demonstrating some of the powerful applications that you can actually build using this framework.
And John had a question on this slide. So your question on this slide, I'm looking at these. You can't see it, but I'm looking at it online. John's question was, where did the quote semantic data sets come from? Are you talking about the semantic data, like Unicode and Violet RDF?
I think that was before I.
Yeah, I don't think he had this.
Oh, he didn't have the examples of it.
Yeah,
Okay.
no, I had those after the fact. I should have resolved that. Sorry.
Okay. Okay. So the community has a lot of these data sets out there. So we basically sucked them in.
Right.
I just
No, that,
resolved it.
well, I think that what's really nice now is that you've got two really good examples. You've got good examples of semantic data and good examples of the structured data, which tie into that architectural model that you just presented. So this is a very good illustration of the architecture. Proceed.
Sure.
So what do you mean orange is visual? Can you go back to the previous one?
Oh, oops.
That one.
Oh, orange in the visual.
Orange in visual. Oh, so you're saying that orange is the ectoderm?
Yes.
Neuroectoderm. Okay.
Yes. Okay. So that's how we've been using the system to date, and what has underlied most of the motivation in its internal design, which then begs the question: how do you actually take the system and start applying it to other things? Because that's kind of the long-term goal here. You want to create kind of a generic template of a framework that you can apply to other interdisciplinary fields. And the way I described it, I hope I kind of conveyed the idea that a lot of these classes that are underlying SemNExT are kind of generic templates for what you would hope to do. Once you start stripping away a lot of aspects of the data model, like the gene definitions, the cluster definitions, you're left with kind of core components that emulate the Provo model, which itself is supposed to be a generic template for addressing the provenance analyses. So the internal data model is easily reusable in other applications. Same thing for the data sources. Once you start creating new definitions for the type of data sources that you want to work with, it's very easy to start generalizing this to new and different applications. This kind of ties in with the idea that you should be using a lot of reusable systems under the surface, and that could actually be a way of creating kind of subversions of this in the future, I would imagine, that are aimed at specific aspects of analysis, just dependent on what kind of systems that you're tying into this in the long term. So this is kind of where I talk about what it would look like if you're just going to go through and build a new application from scratch using the framework. So as I mentioned, you got to decide what data sources you want to work with and what types of analyses you're interested in doing. I mean, that should really be what's driving your application in the first place. So without those, you're kind of dead in the water. So you decide where you're getting your data and what you want to do with that data first and foremost. Once you have that in mind, that's when you can start generating your internal ontology. And the design decisions of that are going to come down largely to the developer. It should absolutely be based on Provo, since that is, again, how we represent things in Python, or at least the model that we're using to represent things in Python. So it makes it a lot easier if you're going to be mapping to these entities that we already have defined. But basically use the internal ontology and use that to map between the different schemas for the data sources that you're going to be working with. After that, that's when it gets down to building the data model objects, which is a little bit nitty gritty. And there's something I'll address at the end about potential next steps with that. But the data model objects will, again, just be mirrors of whatever you're defining inside of the ontology itself. And you'll want to design these with the aspects of the objects in mind that you want to actually evaluate when you feed it over to your analyses. So once you figure out how these results rely on each other and how you want to combine them, that's when you start building the Anteater Objects, which are actually going to reconcile a lot of these mappings that I'm talking about, decide how we're going to combine these results, what's important to attach to these objects that we're feeding to the analyses. That's where kind of the last piece falls into place, which is the analysis objects. And those are just going to be codifications of whatever numerical analyses that you want to do. So if you want to do like k-means clustering, you're going to define that in an R script or a MATLAB script, and then reference that using dereferenceable URI inside of the analysis. And the analysis object should download that particular script, run it using R2Pi, and then feed back the results of that while keeping the provenance attached to the semantic array intact. Once that's done, set up a triple store, load the individuals you're interested in, the ontology, and then build your API calls to use these objects however you had envisioned in your particular situation. And like I mentioned, you're not strictly going to go from annotator to data source to analysis. These are kind of designed to be mixed and matched depending on what you want to be doing with them. This is just kind of the workflow that we've already envisioned.
So if I, just a really dirt simple example, if I had some data set, I guess right now my choices are it's either in a relational data model or it's a web-based. I'm sorry, it's in a triple store. So, but let's say I've got some big table, so maybe I can get it into a relational database and import it in. You'll do the extension, so it's easy to do it as CSV, sure. But anyways, you've got that, and let's say my target is to do a principal component analysis of that.
Okay.
Using this structure. So I'm going to generate the internal ontology. I'm going to somehow model the like the column vectors. You know, so that's what you mean by the internal ontology is sort of model what my variables are, like if they're sensor variables, something like that.
Right.
And then there's build the data model objects, blah blah blah. So I know what my analysis object may look like. You know, with it, if I'm using R to do principal component analysis, it's a pretty straightforward thing. Here's my data frame, send it to it. I get back a data frame, which is my PCA result. So I sort of get that part. I'm wondering what might be the middle part. What am I looking for in terms of the structure of results? Or is my example not really appropriate?
The structure of these.
Yeah, so build data model objects capture the structure of the results from different
okay.
sources must be fed to annotators analyses. That's or is it just sort of the data model object is what I want to have as that representation of my data?
Right. I think if I understand what you're asking,
yeah.
What's the purpose of the data model in getting from your results over to, or getting from your input over to the analysis?
Oh,
maybe.
So it could be stripping away. It could be an intermediate model that strips away. Like if my actual source data had numerical vectors and non-numerical vectors, which PCA can't calculate on, maybe the actual data model that I throw over to the analysis is just the numerical data.
Right.
Okay.
Right.
I mean, that's what you do in that's what you would have to do in the R version of this. If you did this completely in R, you would have to get it all shaped and tidied up to do that. Okay.
Yeah, that's kind of where the semantic array comes in.
Okay.
So you're able to have your numerical data in the same object that you have the provenance attached to, and then say, okay, we're just going to strip the numerical data out of this and feed it over to the R analysis.
Okay.
And we'll hang on to the provenance over here until it gets back.
So I got another question. This is a question that Wade was going to ask. What's the scalability of this? How big can these data sources be?
Phenomenal question. I think I might actually hit on that a little bit. A couple slides.
We can postpone it. So
Yeah, you can postpone us.
we'll come back.
Sounds
Because
good.
we also have to come back to the ontology question.
Yeah.
Okay. So practical use. Right. So the idea of using this particular framework versus this analysis framework or the other is that you're going to want to be able to use this to expand the size of your data sets while maintaining consistency between them, and also be able to resolve any kind of conflicts between these data sets under the surface, depending on what your criteria are. Additionally, the idea is that you might want to build this into another web service that you already have set up. The integration again is very, very simple since you're just firing an HTTP request at this, and then it's returning the results to you in JSON LD. So any kind of web service that's going to be reliant on linked data in just a very simple and clean format would probably benefit from this. Technical challenges. And this is kind of where I start talking, kind of answering your question as far as the scalability. There's, oh God, favorite part. There have been a lot of unforeseen issues with this over the past few months. Like a good portion of this semester was spent actually trying to get the freaking thing to run. Issues with the configuration, SQL tables not loading properly. This, as far as the scalability of the system goes, I think we definitely have a lot of work we have to do yet, just to make it a little more robust, a little more, give it a little more wherewithal. It is possible to crash this thing. It is kind of slow in spots right now. There's more work to be done to make it scalable. For our purposes right now, it does what we want. We have 5 data sets that we're working with. StringDB is held in a Docker container in its entirety, which is pretty impressive considering the size of it.
How big is it?
Off the top of my head, it's not massive. It's like probably 10 gigs or
10 gig?
Yeah. It's pretty big. It's pretty big.
So are you running these in virtual servers? Are you running these in personal machines? What are you running it in? What's the platform?
Oh, they're all in their own separate Docker containers. Just running off of my machine right now.
So on a personal machine.
Yeah.
Well, it's kind of, so is that the intended environment? I mean,
No.
well, so that kind of colors your answer.
Fair enough.
Because if you're not running, a software architecture, if it's not running on the environment that it's meant to be running on, then kind of I mean, it's impressive if you're doing big stuff on a machine that's tiny. Okay, that means that you can then say, well, this will probably scale really nicely on a powerful machine. But if it's intended to run on a server class machine and you're running it on
ThinkPad.
a ThinkPad running Ubuntu with the stupid graphic user interface, you get my point. So if such time you do report on the performance, you need to make sure that you're doing that quantification of the performance on a machine it's intended to be on.
Point made.
But as far as the scalability is concerned, yeah, I think it's really important to understand what the size of these are, when you saddle up with these data sets, because it's really important to know if 10 gig triple stores.
That's a sizable thing. I think it'd be good to annotate the slide with approximate sizes.
Okay. Yeah, I can add that.
Yeah, and in fact, that on that demo, the slide that shows that the microcephaly example, when you're showing identifying those different data sets that you're running, that you're including in, you should annotate that. What each one of those, how big those are, just to give some.
Oh, so you would do that in
when he lists those off. It's the slide with the graphic.
with the graph.
Right.
Yeah. Okay. I'll leave the.
Because he's got the sources named.
Yeah.
So he should just identify.
Well, but he only has a few of the sources. He only has Unicron, BioTarget, Free Drugs, StringDB, Ensemble. Yeah. So he only has some of them. But still, annotate these.
I think it would be really useful to have.
You might make a new slide of the sources and approximate sizes and one fragment of a sentence about what they contain.
All right.
Just got a table or something.
Yeah.
Okay. All right, I'll add that in.
So that's probably a new slide because it wouldn't fit on that other slide.
Right.
But I actually, on the related note, I thought we were going to put this on the server. Why haven't we put it on the server? Is it a problem?
Isn't it running off of one of the servers right now? So I mean, I'm running it from my machine. As far as just having the test environment, I can just tear down every time I change 2 lines of Python.
Oh, okay.
As opposed to having to reboot one of the instances over there.
So the SemNExT.TWed.rpi.edu, I mean, so that has the thing that makes those pretty pictures.
Yeah.
So I thought that also has the content underneath it.
Right. Not the modifications I've been making.
Okay.
Yeah, I want to make sure that's stable and
Yes.
that's working properly before we try and put that one on the servers over there.
Okay.
Yeah. So I guess with regards to running it on a little machine like this, systems isn't really my forte. I would have to talk to somebody who's a little bit stronger with that, like Evan, about the scalability.
Okay. No, so that's, I mean, it's good to know. It also, just as sort of an afterthought on this presentation, you should annotate what is the new work. The work that you're doing versus the sort of the in production now stuff.
Okay.
Yeah, so that should go in paper. I mean, so you've got the guts of the paper here. The new work has to be highlighted. And
Right.
actually, do you have a slide for that? You might not.
I
Let's find
don't
out,
think
'cause I think he's about
I
to
don't
wrap
think
up.
I don't have one that pertains directly to redirects. I could talk a little bit about that.
Okay,
Not
well, I'm putting it on as a comment on the technical challenges.
So-
So got a slide for new work.
okay.
I've been updating your presentation all the way through, but
okay.
since you're not reloading, you're not.
So
getting
did you
them.
add any slides for Michelle?
I didn't add any slide. Well, actually,
Why don't we're getting closer, so why don't we let
That's fast.
get Spencer finish up, or is this it?
Pretty close. I think I have one more slide. Next steps. Okay. Right. So I guess this is where I can talk a little bit about what I've been.
but sorry, before you go on from the technical challenges, you solved the top 3, right? So you had unforeseen issues, but you solved them, or
2 for 3. I'm having an issue with one MySQL. This is weird. One of the SQL tables is temperamental. It won't load sometimes when I spin string DB up. Sometimes it will. Need to investigate a little more. That's why I just haven't torn
So
that
you're
string
loading
in 2 weeks.
So you're loading string DB into MySQL. That's how you're accessing,
Correct.
and that's that 10 gig thing.
what's the scalability of my SQL?
Yeah. Wow. I'm worried about his thing. If he bumps against a memory issue, then right there's your problem, sir.
Could
What if
be.
you just try it on a good machine? I mean, if it's only loading string DB into MySQL, you can put MySQL on some big server.
And there's the next step. Yeah.
I think he needs to fire off a question to Patrick West, Jim McCusker, Stefan Zednick, and Evan, saying, "This is what I'm trying to do. What's wrong with this picture?"
Yeah.
Okay.
And CC John and me.
Yeah.
Great.
Just for the sheer entertainment.
Yeah.
No, seriously. I mean, this is. It could be some kind of a memory capacity issue or something like that. 10 gig is a large.
Yeah, that's sizable.
That's a large thing to load into.
I think it's 10 gigs. I'm pretty certain it is. But
Well, even that, it's just ballpark.
Yeah.
It's still big-ish. Not giant, but big-ish.
Well,
Big
yeah,
enough.
and there may be other ways that you want to deal with such a large data source. So
And McCusker might have already looked at it.
So, for example, part of the purpose of having these kind of architectures is that you've got you've got a legacy or existing data structure already there. Okay, so you're going to have, instead of reloading that every time, it's there, it's operating. I mean, certainly in an enterprise environment, that's what you have. You don't bring it up all the time. It's there. It's an existing thing. It's curated, etc. So a more realistic environment. So even if you were running this locally, okay, what you might want to do is be hitting your MySQL database on a server class machine that's able to serve more efficiently serve that data source. I mean, that's how databases are architected right now, is to be those centralized resources. So you ought to be able to set that thing up and just have it there coming along, and then you hit it over the network rather than.
Right. What I wanted to do at the beginning of the semester that I kind of got distracted from was I was going to put this in an AWS and an Amazon Web Service instance for myself, so that I would be able to just reference these things without having to worry about tearing down StringDB or anything along those lines because of any local issues.
Right.
I didn't want to deal with the time figuring out how to set up a cloud instance. So it's something I could definitely revisit, and I should know for the future
Okay.
for
Well,
when I do these kinds of things again.
That would be a potential solution, is to do it that way. But also, depending upon what you need, we do have resources in the lab where you can do that as well. So
That's true. Okay. Oh, next steps. Right. So I'll just kind of fly through these really quick because we are short for time. But kind of the next few things that we have discussed that need to get done is we would like to embed a rules engine as a part of that underlying architecture. This would make the job of the annotator a little bit easier, I think, as far as deciding when to act on a particular object that you're feeding it based upon its contents. So that would be an important thing to do. We were looking at one rules engine last semester called Pychenko. It's an old rules engine. I don't think it's been updated since 2010, but it's built on Python, so single language stack. That would make the most sense to incorporate. Other than that, I need to find some options as far as reconciling conflicts in data between the different data sets. Because as it stands, a lot of the data from these different data sets pertain to different things. But redrugs and StringDB actually both have data pertaining to gene interactions. And I'm pretty sure that they're different. Some of it's different data. So it's not always going to agree. So we need to figure out a way to make those, to resolve those conflicts when redrugs says this interaction has a particular p-value versus StringDB.